Hi everyone. I'd like to thank the organizers for the opportunity to share some of the work that I've been doing as a postdoc at Oregon State, looking at seasonal variability in the benthic metabolism on the Oregon Shelf. We heard a bit about the Oregon Shelf in Monday's session on deoxygenation, but I wanted to start with refamiliarizing you with our research area. The Oregon Shelf belongs to a unique set of shelves that are within eastern boundary current systems. It is part of the California current system, which is one of 4 such systems located around the globe, and they are home to highly productive ecosystems that support major fisheries. The shelf off the Oregon coast is narrow, generally less than 50 kilometers wide, and has been referred to as a slope-dominated margin, which means that a substantial part of the net production is transported offshore and therefore not tightly coupled to respiration, benthic fluxes, or burial on the shelf. However, there are 2 major banks off central Oregon that broaden the shelf and influence circulation locally. Today I'll be presenting data from 2 sites off of the central Oregon. These sites are located on the well-studied Newport hydrographic line, seen here, which is also the location of the OOI endurance array. The 2 sites are located on the NH line at 30, which is seen here, and 80 meters, which correspond to the inshore and shelf sites on the OOI endurance array. The sediments at these sites is dominated by fine sands, which is shown in this picture here, which is from the very most top part of one of the cores that we took, as shown in the video that Claire showed in the first talk. Sands are permeable sediments, which are which are different than fine-grained, diffusively dominated sediments, and that they're subject to advective flows, and they can then support high rates of remineralization because of enhanced solute and particle exchange between the pore water and the water column. Seasonally, the Oregon coast is subject to upwelling that is driven by the frictional coupling of wind, water, and the Coriolis effect. During periods of sustained winds from the north, Ekman transport moves surface waters away from the coast, and these surface waters are then replaced with water from below. The water that is brought onto the shelf is upwelled from about 100, 150 meters water depth and is lower in oxygen. It is not hypoxic. It is typically around 100, 150 micromoles of oxygen per liter and higher in nutrients. The injection of nutrients onto the shelf can then fuel primary production, and this primary production is eventually remineralized and is broken down and further reduces oxygen in these waters, creating hypoxic areas. This figure, or both these figures are from Pierce et al., but this figure shows monthly oxygen concentrations in the near bottom water at a site 58 meters, a site in 58 meters of water, which is on the Newport line and about half, and it's in between my 2 sites. The circles in this plot show data from 1960 to 1971, and the X's show data from 1998 to 2009. There's a strong seasonality in the oxygen data that corresponds with the upwelling season, which is denoted by these dashed lines, which show the spring transition here and the fall transition here, when wind conditions change from downwelling favorable to upwelling favorable, and then back to downwelling favorable. Hypoxic concentrations are shown in this shaded area here, and often occur between the months of May and September when these upwelling conditions dominate. As you can see from the range of bottom water concentrations, bottom water conditions on the shelf at these depths can change dramatically over the course of the year and are often characterized by hypoxic conditions in the summer months. Another seasonal factor that affects biogeochemical cycles and bottom water oxygen on the Oregon Shelf is wave energy. During the winter, large wind waves that are created from North Pacific storm patterns result in enhanced water column mixing. And here we have some data from 2009 that show significant wave height in meters from the OOI shelf mooring. And you can see that we have large significant wave heights in the winter, and then smaller significant wave heights in the summer. These seasonal physical and biogeochemical processes are reflected in the water column properties on the shelf. Here we have the seasonal profiles taken at 80 meters, so the mid-shelf section for January, spring, summer, and fall. In the winter, the water column in this last panel is very well mixed. We have increased wave energy, and the bottom water is very well oxygenated. However, when the mixing due to the wave action subsides in the spring and upwelling winds prevail, the water column becomes more stratified, as shown here in this panel. By midsummer, the bottom water concentrations have dropped around 50 here, so below hypoxic concentrations, and the productivity is highest in the upper water column. As we near the fall transition, upwelling favorable conditions begin to weaken, and wave energy begins to increase, and then we have weakening in the stratification of the water column. Reduced oxygen concentrations can have adverse effects for growth and metabolism in many marine organisms, and here we have images from Oregon Fish and Wildlife that show 2 fisheries which are of economic importance in the Oregon coast, rockfish and Dungeness crabs. And they are seen here on the shelf at around 150 meters. And you can see in this top left panel what seem like seemingly happy rockfish, and then less happy rockfish and crabs in these bottom panels. So that brings us to our research questions, which were, is there seasonal variability in the benthic oxygen utilization? So are we seeing higher rates of benthic oxygen utilization during these hypoxic events in the summer, or are we seeing them in the winter? What is the contribution of the sediment oxygen utilization to these hypoxic conditions? And then do levels of wave energy and turbulence dictate oxygen utilization in these systems? And we are currently addressing these questions through a series of 10 cruises off the Oregon shelf. We've completed 9 of these to date, and our last cruise will be next month. On these cruises, one of the approaches that we're taking to measuring sediment oxygen utilization is a waterside approach, which Claire and Amelie talked about, called aquatic eddy covariance. This is a non-invasive technique that is used as to not to disturb the advective transport between the sediment and the water column that make these permeable sediments so reactive. And here we have a picture of, I don't want to use the stick. Here we have a picture of one of the 2 benthic landers that we have equipped with our eddy covariance instrumentation. So you can see here that we have the ADV, and then we have a thermistor probe, and then we have an oxygen optode. And these are capable of making simultaneous velocity, oxygen, and heat measurements at 64 hertz or 64 times a second. And here's that same setup deployed on the Oregon shelf. To put our cruises into the scope of local upwelling conditions, I've shown the upwelling index for the last 18 months, which is calculated from wind shear. And then I put an 8-day filter on those daily averages, and that's what's seen here in this black line. So upwelling conditions are favorable when you have a positive number, and downwelling when you have a negative number. And this blue line is the average of these conditions from 1967 to 1991, with the shaded blue area showing the standard deviation of that average. The 9 cruises that we've had so far are shown in red, and they span a variety of upwelling and downwelling conditions over the last 19 months. And for the remainder of this talk, I'm going to focus on the 4 cruises in July, in October 2018, in January and April 2019, as examples of benthic metabolism in winter, spring, summer, and fall. So here is data from a single lander deployment from the mid-shelf site, which is 80 meters, and it's collecting data about 30 centimeters off the sediment water interface. And the data has been reduced from 64 hertz to 8 hertz and was collected during a time of hypoxia, so below 60 micromoles per kilogram. And here we have the processed data calculations, which have been averaged into 15-minute bursts for current speed, significant wave height, and then oxygen fluxes. So it's important to note that the oxygen fluxes are negative. That means consumption of oxygen in this area, and when it's positive, it means production of oxygen in this area. And that from this plot, you can see that we have relatively stable oxygen consumption throughout this time period, but we do have some variation that seems to vary with some of these hydrodynamic drivers. So these are the fluxes that we just looked at. And one of the nice things about the instrumentation that we have is that we have 2 benthic landers. So we were able to put out 2 of these systems at the same time and see how they compare. So these are measurements made by the 2 landers that we have, and they overlapped in time for the summer deployments on the mid-shelf, and they were 650 meters apart. So you can see that the magnitude of these fluxes are pretty similar throughout the deployments, and that the trends, they change pretty well together as well. So these are the 2 deployments that we just looked at, and then these are the rest of the deployments that I'm focusing on today from the Oregon Shelf. So today I'll be showing you 14 eddy covariance deployments, and right now we have 30, and I'm sure we'll collect a couple more next month. So each of these blue or light blue shows a single eddy deployment. This was the data in summer that we just looked at, and then we have data from 2 deployments in winter, 1 in spring, and then 2 in fall. And these are, as far as I know, the first measurements that have been made in winter on the Oregon Shelf. When we look at the data for the inner shelf, we see similar seasonal trends in which we have lower oxygen fluxes in summer and higher oxygen fluxes in winter and fall. Let's see. Oh, so we have some variation throughout these deployments where we have even some positive fluxes in these environments, which we're not really expecting because we don't have light penetration to the sediment floor. But we are capturing potential advective transport with different oxygen signals into this bottom water, which may lead to some of these positive and some of these higher negative flux values. So here I've summarized the benthic oxygen utilization by reducing fluxes to the mean of all the bursts taken during a single season. So the N number represents the number of 15-minute bursts that were summarized in that bar, and the standard deviation is represented by those error bars. And so to answer our first question was, is there seasonal variability in the benthic oxygen utilization? The answer is yes, but it wasn't necessarily what I was expecting, which was that we would have higher sediment oxygen consumption rates in the summer, but we're instead seeing higher oxygen consumption rates in the winter and the fall. So I then wanted to look at how these fluxes compared to other field observations. So I pulled data from the literature along the central Oregon coast. And so the first data that I'm showing here was taken along the Newport line, Strawberry Hill, and off of Hecata Head, and it was collected using benthic chambers from a variety of depths along the shelf. And you can see that there isn't a strong correlation in this data between shelf depth and oxygen consumption. So here is some data collected by Reimers et al. In 2012 using eddy covariance, and that was collected also along Hecata Head, Strawberry Hill, and the Newport line, all at 80 meters. And you can see that these values occur pretty well with the benthic chamber values that were previously measured. And that all of these that I've presented so far were taken during summer conditions. And then Christina began to expand the coverage of oxygen consumption on the shelf by adding the shallower sites here around 30 meters off of the NH line, and also expanding the temporal coverage by showing data that was present from March to October. And then Reimers et al. 2016 also showed off of head-to-head 80 meters oxygen consumption rates that seem to agree well with the other oxygen consumption rates at that depth. So here are our results, and these are from, and what you can see from our results is that the non-winter and the non-fall events, which are not these ones here, agree well with the rest of the studies that have been observing fluxes on the shelf, and that really it isn't until we put our fall and winter fluxes on here that we get to some of these higher consumption rates. So this brings me to one of our potential discussion ideas. So the Oregon Shelf is considered a slope-dominated margin, and if this is true, what do these high fluxes in winter and fall say about organic carbon fluxes being retained versus exported off of the shelf? So are we retaining more carbon on the shelf than we think, or are we truly exporting it all off the shelf? Our fluxes did compare well to field studies, and I also wanted to see how it compared to the model observations. So Sam talked about this model on Monday, but I wanted to remind everyone that the model was presented using summer oxygen budgets of interest to look at the hypoxic conditions in the area. But what you can see is that she has sediment oxygen demand numbers of about -7 to -9 for the Oregon Shelf, which agree well with our numbers, which are shown here. Which are shown here, but then what that means is that we are also in agreement with Sam that the sediment change in the sediment oxygen demand on these during hypoxic conditions in the summer is not really causing the hypoxia, and it's only contributing a small percent, which is probably around 10%, staying in the same type of ballpark numbers that Sam presented in her model. And so the last question was, do levels of wave energy and turbulence dictate oxygen utilization? So is it this pumping of oxygenated water into the sediment that's really fueling this sediment metabolism? And so to do that, I looked at this relationship. I looked at fluxes versus total turbulent kinetic energy. I also looked at significant wave height and current speed. And what you're looking at here is an average of each deployment and grouped by location, so mid-shelf in blue and inner shelf in red. And the error bars represent the range of fluxes as well as the range of conditions that were seen over that 1 to 2 day deployment. And we can see from these relationships that there is some type of relationship between turbulent kinetic energy and oxygen fluxes on the inner shelf, and a very strong relationship between turbulent kinetic energy and oxygen fluxes on the mid-shelf. And when we look at the flux relationship to significant wave height, we see a similar correlation between significant wave height and oxygen fluxes on the inner shelf, and less of a relationship between significant wave height and oxygen fluxes on the mid-shelf, but that these are still all statistically significant. And lastly, I looked at current speed at both locations, and you can see that we have a statistically significant relationship between current speed and oxygen fluxes, but that we have a very weak relationship between current speed and oxygen fluxes on the mid-shelf. So to wrap up with some summary implications, we saw that we had both seasonal and spatial variability in benthic metabolism on the shelf. So we saw highest benthic oxygen consumption in the fall and winter, and lowest sediment oxygen utilization in summer under hypoxic conditions. These summer fluxes compared well with the model results, and they also compared well with the previous non-winter and fall fluxes that were made elsewhere on the shelf. Our results do not imply that the sediment oxygen utilization is a strong driver of drawing down this oxygen during hypoxic times. We did see a strong relationship between benthic oxygen utilization and turbulent kinetic energy and significant wave height at both sites, but no relationship with near bottom currents at our mid-shelf site. And this leads us to believe that the margin may not be a slope-dominated margin, and that there's actually a tighter coupling of carbon production and remineralization on the shelf than previously thought, and that there may be greater importance needs to be paid to the non-summer sediment oxygen utilization throughout the year. And I'll leave you with some data I didn't get to talk about today, which was our sediment core incubations with a very unhappy little crab and sand dollar, and I can also take any questions.
Great. Questions for Kristen?
I get to go first. Hi, I'm Jeremy Testa from UMCs, and your data, thinking about the ratio of water comp consumption to benthic consumption, fits within our sort of cross-system syntheses of how those ratios are. So I'm glad to see my biased worldview is reinforced by your talk. Have you thought about putting like a PCO2 sensor out there? Because I'm thinking about potential for sort of oxygen limitation of oxygen uptake in the summer hypoxic times, and if you might see still higher CO2 fluxes, I guess, at that time.
I think it would be great to look at, so we could look at sediment metabolism not due to oxygen, but I'm not aware of any aquatic CO2 sensors that can measure at the frequency that we would need. If you know of one, I'd love to hear about it, but we would need that.
Okay, hi, I'm Jenny Thomas. I'm a postdoc here at HUI, and I'm just wondering about this relationship between benthic oxygen utilization and TKE and wave height. I don't see you saying that it's a causation, I just see you saying there's a correlation, but it seems to me like maybe that correlation would have to be there if they're both seasonal, like high wave energy and TKE. I might be wrong, but I think they're occurring in the winter when, or the non-summer at least, when there's the high O2 concentration in the water. So I'm just wondering if that's just a relationship that has that isn't about one causing the other, or if you know.
Yeah, so there is crossover between each of these hydrodynamic drivers. So you're asking whether or not the turbulent, if we're basically getting at the same relationship due to the turbulent kinetic energy being related to the significant wave height?
Well, actually, to those both being, or to all of that being strongest in the winter anyway. So like water concentrations are higher in oxygen in the winter, TKE and wave energy are higher in the winter. Is it just because they're both seasonal that you see them correlated? Right. Or is there any causation between that?
I think there is some causation because we're just looking at a balance between how well mixed the water column is, and that is when it's not as mixed, you're seeing the lower oxygen concentration. So when you see that high stratification.
Okay, thanks.
I think the point is, though, that there's more oxygen available to oxidize carbon, both because of mixing and because of higher bottom water oxygen. So they are coupled.
Hi, Julia Moriarty, USGS.
I don't see you. Oh, no.
Great.
Okay.
Great talk. I was curious about, so when you're getting these higher wave and current speeds, you're going to be changing the ripples on the seafloor, which would affect the advection through the sediments. And so I was curious if you've thought about that, how that affects your results, and also in terms of like the area of the seabed that your instruments are looking over. Any thoughts?
So I see that as one of the strengths of using eddy covariance is that we're kind of integrating over larger areas, and so we don't need to necessarily think about, are we capturing a flux at a crest versus a crest at a trough, or a flux at a trough. And these measurements are kind of integrating on tens of hundreds of meters around that area. Does that answer your question?
Yeah, and if you have different ripples, you think part of the effect could
I think it all plays in, the turbulence that creates those ripples and the trapping of organic matter, and then resuspension vents is a whole other part of that. So yes, it's all related.